What exactly is an electric circuit? A heating element connected to an electrochemical cell is one type of simple electric circuit. The chemical energy provided by the cell is transported to the heating element, where it is transformed into light and heat. This transformation is carried out by the electrons as they flow from the negatively charged electrode to the heating element and back to the positive electrode of the cell. In a circuit, incredibly large numbers of electrons will pass a specific point in a few seconds. It is therefore simpler to visualize charge in units called coulombs. 1 coulomb of negative charge is equivalent to 6.25 times 10 to the power of 18 electrons. An important characteristic of an electrical circuit is the rate at which the charge flows through it. The rate of charge flow is called current and is measured in amperes. A current of 1 ampere means that 1 coulomb of charge passes a specific point each second. Another concept that helps us describe a circuit is potential difference. The potential difference between any 2 points in a circuit is measured in volts. It is simply the number of joules of energy per coulomb that is changed to some other form of energy as the charge flows from one point to another. We could, for example, measure the potential difference across the heating element and note that it's 1.5 volts. This means that as 1 coulomb of charge flows from one end of the element to the other, it gives up 1.5 joules of energy. The potential difference between the 2 points is simply the number of joules transformed as the charge flows from one point to another, divided by the number of coulombs of charge involved. To complete our understanding of a simple circuit, we need to consider one more factor. Have you ever wondered why the metal making up the heating element gets hot, while the connecting wires stay cool? The secret lies in the fact that the connecting wires are much better conductors than the heating element. The heating element is a conductor, but not a very good one, and is therefore referred to as a resistor. It's represented like this in the circuit diagram. But just how does a resistor differ from a conductor? Let's examine the difference at the atomic level. A resistor will consist of a network of atoms. If the resistor is made of the alloy nichrome, there will be 3 metals present: nickel, chromium, and iron. The arrangement of atoms is similar to that of copper, which we examined in a previous program. We visualized a conductor, like copper, as a network of positively charged ions, which can vibrate but not move about freely. Within this network, there are loosely held electrons, which can drift about with relative ease. In the case of nichrome, the structure is similar. There are, however, fewer loosely held electrons, because the electrons of some atoms are involved in bonds with different atoms. In a conductor, a very small potential difference placed across the ends of the metal will cause a significant flow of electrons from the negative to the positive end. In nichrome, there are fewer loose electrons, and the bonds restrict the number of pathways for these electrons to flow. As a result, a greater potential difference is required to get the charge to flow. Also, the moving electrons collide with ions, causing them to vibrate. Although we can't see that vibration with our eyes, atomic theory tells us that the increased vibration at the atomic level will result in an increase in the temperature of the material. Even a good conductor like copper will begin to heat up if the current is increased substantially. But in most circuits, copper does not act as a resistor, but as a conductor. When we measure the potential difference across any copper connecting wire, we will find that it is very close to zero. Very little energy is transferred to the wires. As a result, the potential difference across the resistor is almost identical to the reading across the battery. Almost all of the transformation from electrical energy to heat and light occurs in the resistor. The resistance of the resistor is defined in terms of the current passing through it and the potential difference across it. By adding more cells, we can change the potential difference across the resistor. Note, when this is done, the current flowing through the resistor is also increased. If we record the potential difference and the current through the resistor, each time we change the number of cells, we find that a straight line results. Taking the increase in potential difference anywhere along this line and dividing it by the corresponding increase in current, we'll always calculate the same value in volts per ampere. A volt per ampere is called an ohm, often shown like this. So our heating element is a 15 ohm resistor. The resistance of a resistor is a special characteristic that doesn't change when it's placed in another circuit. To get a current of 1 ampere to flow through a 15 ohm resistor will take a potential difference of 15 volts. In a circuit with a potential difference of only 1.5 volts, the current will be 0.1 amperes. With this background, let's have another look at our parachutist on the power line. Since the material making up the wire is a good conductor, the potential difference across the short length of wire will be very small. A low potential difference between the two hands is not enough to overcome the higher resistance in the pathway through the body. So, there is very little current flow through the body, and he feels no shock. When he touches the tower, however, there is a very high potential difference across a portion of his body. That is enough to allow a substantial current to flow. The message for all of us: never allow a high potential difference between two parts of your body. That will allow a current to flow through you, the resistor. It doesn't take much. As little as 0.01 amps can cause convulsions, and 0.1 amps, death. With a little knowledge of electricity, we can all keep jumping.